Hi, welcome to my channel, JaberTime, where I do math videos from algebra to calculus and differential equations, simplified with examples. If you like this video, hit the like button and subscribe. If you have any comments or questions, leave them down below. And once again, I want to thank you for watching and hope to see you again and again. Thank you. Let's talk about maxima and minima. Absolute maximum and minimum. Let f be defined on a set D as domain containing C. So Cx like x, some variable, some value for x. If f of C is greater than or equal f of x for every x in the domain D, then f of C is an absolute maximum. Because it's above everyone, it's the greatest, it's greater than or equal for every x. On the other hand, if f of C is less than or equal to f of x for every x in the domain, we call it absolute minimum. See the word every x, that's what makes it absolute. Now, those definitions and what I'm gonna go over are needed. I can't skip them and like last section or last video, just straightforward to the examples, but you're gonna see enough examples and enough graphs. But I'm trying to highlight the main thing and show you what we're gonna be talking about. An absolute extreme value is either an absolute maximum or an absolute minimum. In short, we call them absolute extreme values. Let's look at the graph. Y equals negative x, already factored, times x minus 12, defined on all real numbers. I just want to support why it's going here and here. The zeros are 12 and 0, and it's upside down. Negative is making it concave down. And the vertex will be in the middle, and if you plug in 6 you get 4. So knowing enough about parabolas and how to graph it, look at this graph all the way down, this is the max, but it's the absolute max, not just max. Alright, we call it the absolute maximum value. Absolute, let me read it from my notes, absolute max of 4 at x equals 6. That's a formal way of saying it. Let's take another example. This graph is defined on a closed interval from 5 to 8. Closed here, defined, closed here, defined. I don't want to take your time and show you why this one graphed this way. The point is focusing on max and min and absolute min and max. So because we are just between 5 and 8, it stops right here and stops right here. 5 is taking you to 9 and 8 is on the x-axis. Look at this one here. It's going to be called absolute max of 9 at x equals 5. Here, absolute min of 0 at x equals 8. There is nothing above this one, there is nothing below this. That's why we call them absolute. Here's another example. In this case, it's open from 8. Okay, same problem, but it's open, meaning there is no answer when x equals 8. You still have an absolute max, which we agree on, but no absolute minimum. You get close to this, but there is no point to look at it and point to it and say like there is no more points after that. Alright, that's a limit concept. Like if I ask you questions like this, how many points between 0 and 1? Infinitely many. If you get close to 0 from right, you could say like 0.1 is the closest one. I go like, no. 0.1 divide by 2, take half of that, you're still there. Take half of that again, you're still there. So you can't reach a minimum point right here. That's why there is no absolute minimum. Another example. This time I have it open from the left and closed from the right. So I have no absolute max and I have absolute min. How about if it's open from both sides? Open from both sides. No absolute max, no absolute min. Different example. This is closed. This is open, but it's defined somewhere else. Aligned, all right? Absolute minimum of 3 at x equals 2. Absolute maximum of 10 at x equals 6. Yeah, we have a value of 10. Yeah, we do. And nothing is above 10 that we have. So that's called absolute max. Another example. Maybe we're going down this way. Here, there is no absolute max. If you point to this point, I will say there's another point closer, and so on. There is no point that you could point to and say like, this is my maximum. So there is no absolute max. This one we clearly agree on as absolute minimum. I added another comment in black this time. It's not part of this examples and topic that I covered, but it's within our notes. This point is called local minimum of 9 at x equals 9. See, 9 goes up to 9. Why it's local minimum? Because there is nothing in its neighborhood, they call it nearby, that is lower than this. So we call it local. This one is a local also because next to it, it's the smallest. This one next to it, it's the smallest. They are both local, but this is the lowest of all the local minimums. We call it the absolute minimum. Beneath this level, there is nothing down here. That's called the absolute minimum. So that's the difference between local minimum and absolute minimum. Let me explain that in more in depth in a different graph. This graph goes up, down, up, down, up, down. Close, closed. This is an edge, a corner point. Smooth, smooth, smooth. Here we have a horizontal tangent. We could see that this is a max, local max. This is a local max. This is a local max, but has a better name for it. We call it absolute max. It's not just a local max. It's an absolute max. Above this level, there is nothing. All right? No greater value of f on a to g. I don't want to call it a and b. A to g, that's my interval. No greater value of f on a to g, also local max. We could call it local max, but we prefer to call it absolute max. Just by calling it absolute max, it is a local max. It's the max nearby. Between and this point, let's say, and this point, it's the highest, the greatest value that we have. This point right here, if you notice, it's the lower than this. Absolute minimum, that's an absolute minimum. No smaller value of f on the closed interval, and also you could call it local minimum. But you don't want to call it both ways. By saying absolute minimum, it covers both. This one here is a local minimum. No smaller value of f nearby. Next to it, it's the smallest. This one is local max. I can't call it absolute max because that's the absolute max, because no greater value nearby. It's the greatest nearby, or in an open interval next to it. This is a local minimum. It's not an absolute minimum. This is a local minimum. It's not an absolute minimum. Now let me add more. The extreme value theorem says things that we're going to cover. F prime at b equals 0. Here's b. F prime at this point is 0. We have a horizontal tangent. So we'll look at the definition in just a few seconds, but since I have it, I'll give it to you. Here, it's a critical point. That's another thing in this video. EVT for extreme value theorem and critical points that you need to know. Critical points are points inside your interval, not including the end points A and G, such that f prime is 0 or undefined. F prime here is 0. F prime here is undefined. F prime here is 0. F prime here is 0. F prime here is undefined. So we have critical points as on B and C and D and E and F. This is not critical point. This is not critical point. This is where some students make a mistake. They think all the points are critical points. No, you have to be inside, not including the endpoints. Let's talk about the extreme value theorem. What is the extreme value theorem? A function that is continuous on a closed interval. We saw a graph and we took our time looking at it. Has an absolute maximum and an absolute minimum value on the interval. You're guaranteed to have an absolute max and absolute min. Well, it does make sense. If you start from this point to this point, smooth without disconnecting, it's continuous. You're going to be forced to have a max, and you're going to be forced to have a min. Local maximum and local minimum, which I covered through the graphs, but as notes. What are they? Suppose C is an interior point of some interval I on which f is defined. If f of C is greater than or equal to f of x for all x in I, then f of C is called local maximum. Now this is an interval next to C, including C. That's different than D as a domain. Interior point of some interval I. All right. If f of C is less than or equal to f of x for all x in I, then f of C is a local minimum. Local extreme value theorem. If f has a local maximum or minimum value at a point where x equals C, and f prime exists, then f prime should be 0. We saw that on the graph when it was curving and smoothly moving around. What this says in a different way, it says the following. F of C is a local max or local min, and also f prime exists, then f prime has to be 0. That means you have a horizontal tangent. Critical points. What's critical points? I did mention it, but here's in writing. An interior point, C of the domain of f, at which f prime equals 0, or f prime fails to exist is called critical point. I mentioned that earlier, and I skipped the endpoints. Note, the converse of the local extreme value theorem is not necessarily true. What do I mean? Going back, that's called converse. That doesn't happen usually, or it's not guaranteed. It could happen, but you have to be careful. It doesn't mean like if f prime is 0, you have this and you have this. That's the meaning. Here's a good example. A cubic, instead of graphing it here, I graphed it in the first quadrant, like shifted right and up. At this level, f prime is 0. So we are here. I can't go backwards and say, oh, I have a maximum or minimum. No. But no local maximum or minimum at x equals a. There is no max or min. So by knowing that f prime is 0, it doesn't mean that you have a max or min. Another comment, just to have to be careful. You have to be careful understanding the graphs and following the exact wording and the details in those theorems. Here's just another comment, separate graph. This graph right here, this line is a vertical tangent. What's a slope? Slopes, you can say like the slope is infinity. We say f prime at this point B does not exist. Also, no local max or min. So you just have to be careful. Example: find the critical points of the following function: y equals 3x to the second minus 4x plus 2. Y prime equals 6x minus 4. Set it equal to 0. Now I'm getting into practical examples instead of just looking at graphs only. Here we go. Do the math. Add 4 to both sides, divide by 6, simplify, you get 2/3. So x equals 2/3 is the only critical point, because this is a parabola that is defined on all real numbers. They're not telling me that I'm just defining it from 1 to 5. So I don't have endpoints also to worry about. For other things, inside I do have f prime exists. It's not like it doesn't exist. And 2/3 is the answer. Another example. Doesn't have to be simple and polynomial. 1 over x plus ln x. How do you find f prime here? Well, one way to do this is you put this up, becomes x to the power minus 1, and you move on. Ln x is part of what calculus students should know, so you should know this. And the answer is for this 1 over x. The answer for this is negative 1 over x to the second. Now we want f prime to be 0. We cannot leave it this way, so we're going to combine them with common denominator, x to the second. A fraction like this will be 0 when the numerator is 0. That is when x equals 1. And that's the only critical point that we have. So we are done. X to the second multiplied by square root of x plus 5. How do you find f prime here? Product rule. Derivative, keep as is, keep as is, derivative. This is x plus 5 to the power half. And that's how it came out to be after you bring the half up front. Simplify. We need to combine these two. The denominator here is 2 times the square root of x plus 5. The denominator here should be the same, so I'm going to bring it here. When you multiply top and bottom side by 2 times square root of x plus 5, this 2 becomes 4 on top, and this with this next to it will make it without square root. It's going to be square. Make them one fraction. this f prime will be 0 when the numerator is 0, which means 5x to the second plus 20x is 0. Let's factor 5 out and factor one of the x's out. This way we could find that both zeros, which is 0 and -4. That should do it for this problem. So the critical points are 0 and -4. One more. Determine the location and value of the absolute extreme values of f on the given interval if they exist. Now we have a closed interval. Second degree, closed interval. F prime is 2x. Set it equal to 0. I get x equals 0. So we have a critical point at x equals 0. Now, since we want to find the extreme values, max, min, absolute max, absolute min, local min, and we have a closed interval, this time we need to consider the endpoints. We have inside a 0 somewhere, so we found some kind of turning point inside. I need to find the values at the endpoints f of -2 and f of 0 and f of 3. Because they're negatives, it's a little bit hard to decide quickly which one is the greatest, which one is the smallest, and so on, but I'll support that with a graph, even though they're not asking me to graph. So, we have a local max at -6. We have an absolute min at -10, of -10, I mean. We have an absolute max of -1 at 3. That's how I should say it. Let me support why this is a local max, even though it's negative number. We're going from -2 to 3, closed, closed, opens up, shifted down 10 units, down to 10. That's an absolute min of -10 at x equals 0. That's a local max. That's a local max. And that's an absolute max of -1 at x equals 3. Of -1 at x equals 3. Another example. Determine the location and value of the absolute extreme values of f on the given interval if they exist. A fourth degree one, polynomial, from -1 to 3. F prime becomes 4x cubed minus 12x to the second plus 8x. Just regular derivatives. We're gonna clean it up. So I'm gonna take from all of them 4 out and one of the x's out. This one factors also 2x minus 2 and x minus 1. Set the whole thing equal to 0. That's how we do it. F prime, factor, set it equal to 0. If it's fractions, combine them. I get 3 critical points at 0 and at 1 and at 2. I know 2 came first in my factoring, but it's cleaner to write 0, 1, 2 instead of 0, 2, 1. No big deal, but that's what we have. Now, so I have inside 3 critical points, but because I need to find the extreme values, I need to consider the endpoints also. Saving you some time, I found the values just by plugging in the numbers and the start point and end point, -1 and 3, 0, 1, 2, 0, 1, 2. Here's the values. You could go back and forth and look at them, but let me give you the answers. Absolute max, because they are the same, there is nothing higher than 9, so they're both called absolute max. Absolute min. This one is a local max. You don't need the graph, but I want to support with a graph. If you graph this 4th degree one, opens up, that's how we call it, and it has enough terms, so it's going to have 4 pieces, 1, 2, 3, 4, absolute max, absolute max, absolute min, local max. That should do it. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.